Pilot, here I come.
Okay, so we're basically done with a whole section of this class. Like, we're done defining stress and strain. Almost all of what's left is calculating the stress in specific loading situations, you know? So we haven't done that yet. Like, what happens if you have a beam and it has a force pushing down on it and something stretching it and something twisting it? What are the stresses in the beam? And that's what we're going to do now. And I'm going to just keep making you, so we're going to calculate the stresses, and then I'm going to just keep making you go back and calculate, okay, now what's the stress in this new coordinate system? What's the strain? What are the principal stresses? What's the max shear stress? But that's all, like all that old stuff we're just going to keep doing. But really the new stuff is just figuring out what the stress is. This will depend heavily on Saint Venant's principle. Saint Venant, some French guy, he had a principle, not a school principle. So this one is Principle, exactly. Your school principle makes you work. The other one lets you play. Okay, so Saint Venant's principle. So Saint Venant's principle, so here's kind of the idea of it. So let's think of beams that are loaded two different ways. Two different ways, but similar. So let's say we have these two identical beams. And the one on the left is loaded by point forces like this. And the one on the right is loaded by distributed loads that have the same total value F. So this also is F and F, okay? But if you imagine this being a flexible enough material that you can visualize the deformations that would happen, they would deform differently, right? This one would stretch out where that point force is applied. This one would stretch more evenly because of the distributed load. And it would be nice for us if we could treat these two things the same way. If we didn't have to make a distinction about how those forces were applied. And so Saint Venant's principle sort of allows us to do that. So Saint Venant's principle says, as long, I think the wording might not have been this exactly, but as long as you don't consider points too close to the loaded face, um, the stresses are the same for an equipolant system. So in other words, as long as you don't trust your answers right where those forces are being applied, you can replace any load you want with an equipolant system on that face, and it'll give you good answers. So basically, like we're not gonna trust anything that happens here or here, but for the rest of it, those answers are perfectly valid. How close is too close? This is just kind of a rule of thumb, but it's helpful. Think of about the longest dimension of the loaded face. About the longest dimension of the loaded face. Okay, so you can see that the red shaded area that I gave, the length of that red shaded area is somewhere in the ballpark of the length of that face in the other dimension, you know? Yes?
So St. Bernard's principle is only for beams?
It's St. Venant's principle.
Venant's.
So that's a really good question, and yes, actually, that I was going to give an example showing, you know, so yeah, if the loaded face is, you know, on the same order of length as the other faces, then this is not useful. That's right. So think about a case where you're trying to replace this with this. Since every point on the beam on the body is within you know, one length dimension of the loaded face. In this case, this would give no useful answers. Anybody have any questions about that? If you ever write St. Bernard's principle on a quiz or something, so help me God.
Dismissal.
Yeah, exactly. Right. Okay, so now the first, we're going to get into basically starting at the simplest and work our way up to more complicated cases. So the first cases we're going to consider are members in pure tension or compression. And so let's think of a long, slender member with circular cross sections. And we're going to have forces F like this. This is the cross-sectional area. I'll call that A. Remember that our answers are not going to be valid close to the endpoints. And let's do this with, you don't have to use this coordinate system, but let's think of this as X, Y, and Z. Then the only non-zero stress is the X normal stress. And that is equal to, I mean, this is just like a tensile test, so this result won't surprise you. This is equal to F divided by A.
Is there a reason that you chose that specific coordinate system?
No, you could choose any coordinate system. I guess I usually choose.
Just X along?
I guess I probably chose it because that's how we do the tensile test.
Okay.
But if I had chosen X to the right, Y up, and Z that way, then we would have just had a YY normal stress. Okay, so let's think of a case like this, where we have 5,000 newtons pushing, and the radius of this is 1 centimeter. Then sigma xx is equal to, so tension is positive, compression is negative. So this is going to be negative 5,000 divided by pi times 0.01 squared. And that gives negative 1.59 times 10 to the 7 pascals.
So does it not matter that there's force on both sides, or sort of
Remember that,
law situation?
yeah, it is a Newton's third law situation. I mean, what that is remember that the negative faces of the stress cube are always the opposite of the positive faces. So,
Right, otherwise it would fly off.
yeah, exactly, right. Okay, so the stress tensor here is negative 1.59 times 10 to the 7, zeros everywhere else. This is in pascals. And then to draw the corresponding stress cube, just because of the way I chose my axes to be directed and the way we usually draw the stress cube, it's actually going this way, 1.59 times 10 to the 7. Okay, so remember that positive forces are tensions and negative are compressions. the people who took statics, remember we talked about one kind of structure in statics where every member is in pure tension or compression. Do you remember what that is?
Truss.
A truss, yep, exactly. So we're going to do some calculations where we're calculating the stresses in trusses. So every member is in pure tension or compression. So in order for that to happen, for every member to be in pure tension or compression, it requires that every member is a two-force member. And that requires two things. The first one is the weight has to be neglected. So if weight makes up an important part of what's going on in a structure, you can't treat it as a truss. And the second one is that all loads have to happen at the joints. If these conditions are met, treat each member as a cable. So let's say as a cable in tension. And then use Newton's second law on each joint. Negative tension values. If you get a negative value, then just means that that member is in compression, not tension. Obviously, cables can't support compression, but these things can. So negative tension values mean compression. Okay, let's do an example. And let's say so let's say we have this isosceles triangle. That's connected to the ground by two pin joints. And there's a pin joint connecting these two here. Come on. And let's say the lengths of each of them are 1 meter. Let's make this 70 degrees, 70 degrees. And it needs to be able to support a horizontal force of let's say 2,000 newtons. and say we want to know what's the smallest cross-sectional area so that the maximum shear stress stays under, let's say, 1 times 10 to the 7th pascals. Okay, like this is a pretty reasonable, like the kind of thing you could easily imagine being a design requirement for something that you're building. Okay, so how are we going to do this? Well, we're going to calculate we're going to solve this truss. We're going to calculate those internal tension compressions. Then we're going to come up with an expression for the tension and compression stress that includes that area. And then we're going to use the principal stress thing and calculate the maximum, and then eventually we'll be able to calculate that area. Can everyone sort of see your way roughly through how we're doing this? Okay, so the first thing we have to do is solve this truss. So I'm going to call these joints A, B, C. And I'm going to start with B. I think that's the only one we're going to need. And the free body diagram, we have a 2,000 Newton force this way. Oh, and I'm going to name these members. I'll call this one 1 and this one 2. Okay, so if 1 is in tension, we're always going to assume that these members are in tension. It's going to apply a force this way. I'll call that F1. And if 2 is in tension, it's going to apply a force this way. I'll call that F2. And those are all the forces applied to that pin, applied to that joint. And now Newton's second law says, okay, this one is, so 70. So let's think about these angles for a second. So here's the coordinate system. We know, well, I'm going to do it like this. So we know that this is 70 degrees. And then we know that it's 180 from this one to this one. And so my angle there is positive 70 plus another 180. So I'm going to use positive 250 as my angle. So Newton's second law says F1 times cosine of 250 sine of 250 plus F2, and this is just cosine and sine of negative 70, plus 2,000 0 is equal to zeros. So let's see, negative 0.342 F1 plus 0.342 F2 is equal to negative 2,000. And negative 0.940 F1 minus 0.940 F1, F2 is equal to 0. And so here's our system of equations. We get that F1, let me write it as F2 is equal to negative F1. Plug that into the first one, and you get negative 0.684 F1 is equal to negative 2,000. So F1 is equal to, what do you get there?
2923.8.
2923.8. Yep. And that means that F2 is the opposite of that, so negative 2923.8. If you look at how this works, you can kind of make sense out of the fact that this one is going to be in tension and this one is going to be in compression. Okay. And so now let's go through the two. So I'm going to start with member 1. The answers are going to be the same for the two members because the absolute values are the same, but you don't have to recognize that. Okay, so I'm going to call sigma xx 2923.8 divided by this cross-sectional area A. And so I can write the stress tensor as 2923.8 over A, and then zeros everywhere else. And in order to come up with an expression for the maximum shear stress, we need a principal stress tensor. How hard is it to get a principal stress tensor from this?
Super easy.
Yes, exactly. You already have, this is already a principal stress tensor. And so now we can just say that, so we're going to take, for our maximum shear stress, we're going to take the maximum principal stress, that's 2923.8 over A, minus the minimum. Well, the middle and the minimum are the same, so this is just minus A. And then divide by 2. And so you get, well, can you divide that by 2 for me? 1, 9, 6, 2.9.
1461.
Ah, fuck.
You hadn't said it, you almost could have faked that 9 was a 4.
That's true.
Sort of draw.
0.4?
0.9.
Oh, 0.9. Yeah. I'm on tilt now. Okay, so there's the maximum shear stress. And now we want to set that equal to a maximum value of 1 times 10 to the 7. So 1461.9 over A is equal to 1 times 10 to the 7. And so A is equal to 1, 2, 3, 4, 0.000146619, I think. 14619 times 10 to the minus 4 meters squared. Okay. Any questions about that? And doing the other one, you know, since we got that those are equal and opposite values, so member 2, we would have a stress tensor that is negative 29, 23.8 over A. And the only difference for this one is you would go, like when you're calculating the maximum shear stress. Now the maximum principal stress is 0, and we're subtracting this negative 29, 23.8 over A. And you get the same thing out. You get 1461.9 over A. And then A comes out to be the same thing.
So in these cases where it's like uniaxial, like I remember where you said it's like when you're like rotating about the middle, you can just choose either one that's 0, and it'll give you the.
That's right, exactly. Yes. So if you wanted to, if you were skeptical and you wanted to come up with a stress tensor that had this maximum value in it, it could be positive or negative, but the absolute value shows up. You could do a coordinate system transformation of this stress tensor about the y-axis or about the z-axis, and you'll get the same thing. I mean, in one there'll be positives, in one there'll be negatives, in one they'll change what shear spot they're in.
Which
but
totally makes sense if you think about it.
Yeah, right. Yes.
Because turning a cube from one face or another doesn't.
Yes.
Just puts the top on the side.
Exactly. Exactly. Okay. Anyone have any questions about that? So I think my plan is just to make you do some truss calculations. One thing, the people who took statics with me did this a million times, but sometimes you get big systems of equations with these. So I do want to do one. I'm not going to go through the full example, but let's say we have, so let's say we have an equilateral triangle now. And now we have 3 members. All the angles are 60 degrees. And all the lengths, let's say, are 1 meter again. And let's do the same thing again. Let's just have a sideways force like this. Well, let's do another one too. Let's have this one going 1,000. And let's say that the cross-sectional area for all of these is 0.001 meters squared. And we want to calculate the maximum shear stress for each member. Okay, so I'm going to label these joints A, B, C, and the members 1, 2, 3. And I'm going to start with B. So free body diagram of B. We have F1 there, F2 there, and 1,000 here. Bless you. And so Newton's second law says, so this is, I guess the way I have this set up, we can solve this just joint by joint as we go. But instead, let me just come up with a system of equations, and then I'll show you how to do reduced row echelon form in your calculator to get that. So this first one says we have 1,000, 0, plus negative 0.866 F1, negative 0.5 F1, plus, I did those backwards, sorry. This should be negative 0.5 for the X component, and negative 0.866 for the Y component. And then we have positive 0.5 F2 for the X component, negative 0.866 F2 for the Y component. And all that's equal to zeros. So we have two equations. The first one says negative 0.5 F1 plus 0.5 F2 is equal to negative 1,000. And the second one says negative 0.866 F1 minus 0.866 F2 is equal to 0. And then we'll go to C. So that one we have 1,000 Newton force this way. We have F3 also pulling this way. And we have F2 pulling this way. And one more thing, we have the ground pushing up on the roller of this joint. So I'll call this RC. And so Newton's second law here says negative 1,000, 0, plus negative F3, 0, plus negative 0.5 F2, positive 0.866 F2, plus 0 RC is equal to zeros. And so our next two equations, our third equation says, I'm going to reorder these, negative 0.5 F2 minus F3 is equal to positive 1,000. And our fourth equation says 0.866 F2 plus RC is equal to 0. And now we have four equations for four variables. And this technique works for, so 4 is kind of getting towards the limit of what you'd want to do by substitution or whatever. You can easily, with trusses, come up with, 30 equations, 30 variables. You definitely don't want to do that by hand. But reduced row echelon form will always let you calculate that. So the way you want to do this, so this is reduced row echelon form. And on your calculators, it's always called RREF. And so what you're going to do is set up a matrix with the number of rows equal to the number of equations. So in our case, that's 4 rows and one more column than row. So 5 columns. So this is the number of equations. This is the number of equations plus 1. And I'm going to choose an order for my variables, and then the constants are going to be this last one. And for my variables, I'm going to call it F1, then F2, then F3, then RC, but it doesn't matter what order you do them in. The answers will just come out in the order you chose. And one thing you have to remember about these constants is those have to be alone on their own side of the equation. Okay, so let's go through and we're just going to put the coefficients of all these things in these places. And this will be our equation 1, equation 2, equation 3, and equation 4. So equation 1 says F1s, we have negative 0.5. F2s, we have 0.5. And the constant on its own side of the equation is negative 1,000. And everything else is zeros. Equation 2, F1s, we have negative 0.866. F2s, we have negative 0.866. And everything else is zeros. Equation 3, F2s, we have negative 0.5. F3s, we have negative 1. Constants, we have positive 1,000. And then zeros. And then the last equation says F2s, we have 0.866. RCs, we have 1. Everything else is zeros. And so if you make this matrix in your calculator and then find the function RREF and run it on this matrix, it'll give you something back that says, so it'll give you a matrix back that's the same size as what you put in. And for the first, so it's going to have an identity matrix like this that doesn't make it to the last row. Just ones in the main diagonal, zeros everywhere else. And then the last row is going to be your answers in the order that you chose. So in this case, it's going to give you 1,000, 500, negative 1,000, and 866. With the TI-84, I think you'll find that RREF function, if you go to matrix, go to the matrix environment and then go to math inside the matrix environment, RREF is in that list. But this is just always a nice thing for solving big systems of equations. If you ever run RREF and it spits out something that doesn't have this identity matrix in this first part, then something went wrong and those answers are wrong. Okay. So these are the answers. And they're given in the order you chose. Okay, well, I said we were going to calculate the max shear stress, but let's just stop there on this one. Yeah?
What did you set as your second variable?
F2.
I'm pretty sure F2 is negative 1,000. Because our second equation was basically that F1 needs to be negative F2.
They need to be equal to each other. Oh yeah, I probably chose the, you're right, that's a, yeah, good point. Let's see. Yes. In my notes here, I have them numbered differently. That's why it came out different. So F2 should be negative 1,000. And then was this negative 500?
Yeah.
Okay, thank you. Oh, and then this, is that?
Is that the same with the one above?
With the one above?
Is that, no, like that same one down a little bit? One more. That one. Was that the same table we were just looking at?
Yeah.
Okay, all right. Sorry, I got confused.
Yes.
What's the table under that one?
This, and then once you run reduced row echelon form, this is the answer it'll give you.
I got it.
And basically think of the stuff in red as just telling you whether it worked or not. And then the stuff in green are the answers.
I see.